Imagine standing at the edge of our solar system, gazing into the vast cosmic ocean that separates us from the nearest star. 4 light-years of emptiness stretch before you, a distance so immense that light itself, the fastest entity we know, takes years to cross. Now, picture yourself wanting to visit that star. Our most advanced spacecraft would need thousands of years to make the journey, rendering interstellar exploration seemingly impossible within a human lifetime. Yet in laboratories across the world, theoretical physicists are quietly working on concepts that may fundamentally rewrite our understanding of cosmic travel. They speak in hushed tones of wormholes, warp bubbles, and quantum tunneling. These aren't the familiar tropes of science fiction, but emerging theories built upon the mathematical foundations of our universe. Theories that suggest the seemingly impossible might merely be waiting for the right insight. Einstein's century-old declaration that nothing can travel faster than light has long stood as an immovable cosmic speed limit. But what if there were loopholes in the very fabric of reality? What if we could bend the rules without breaking them? The universe is vast beyond comprehension. Our galaxy alone contains hundreds of billions of stars, many harboring planets potentially similar to Earth. Yet they remain forever beyond our reach if we cannot overcome the tyranny of distance. Tonight, we explore the cutting-edge physics that suggests faster-than-light travel may not only be possible, but might be woven into the fundamental structure of space-time itself. We'll examine theories that were once dismissed but are now being reconsidered. Recent breakthroughs in quantum physics have revealed strange connections that defy our intuitive understanding of distance and time. Particles can influence each other instantly across any span of space, suggesting deeper principles waiting to be understood. Some physicists now propose that we've been approaching the problem incorrectly. Perhaps the key isn't to travel faster than light, but to manipulate the very medium through which we travel, to compress space ahead and expand it behind. This isn't mere speculation. Mathematical models supporting these concepts have passed initial theoretical tests. The equations suggest possibilities that, while challenging to achieve, don't violate the fundamental laws of physics as we understand them. What if interstellar and even intergalactic travel could be accomplished within human lifespans? What would it mean for our species to have access to thousands or millions of worlds rather than just one? The implications reach far beyond transportation. A revolution in our understanding of space-time could transform our comprehension of the universe's birth, its eventual fate, and our place within the cosmic story. Tonight, we'll journey through the history of humanity's quest to overcome cosmic distances. From early maritime explorers who crossed oceans to modern physicists who might help us cross the stars, we'll separate established science from speculation. We'll explore concepts that sound impossible but are being seriously considered by respected scientists. Ideas like the Alcubierre drive, which proposes warping space itself to achieve effective faster-than-light travel while technically never breaking Einstein's speed limit. We'll examine the quantum phenomena that hint at deeper truths about space and time, truths that might ultimately free us from our cosmic isolation and connect us to the wider universe that has remained tantalizingly out of reach. The story begins with Einstein's revolutionary understanding of space and time, continues through decades of theoretical work, and brings us to today's laboratories, where experiments probe the very limits of our understanding. You'll discover why some of the most respected physicists in the world believe that faster-than-light travel might not only be possible, but inevitable as our understanding deepens. And you'll learn what obstacles still stand in our way. The quest to transcend light speed is more than a technical challenge. It's a philosophical journey that forces us to reconsider our conception of space, time, and possibility itself. It pushes us to the edge of knowledge, where certainty dissolves. Tonight, we delve into this mystery at the frontier of physics, examining the theories that could transform humanity from a single-planet species into explorers of the cosmos. We'll separate established science from speculation, possibility from fantasy. By the time we're finished, you'll understand why some scientists now believe that the seemingly insurmountable barrier of the speed of light may ultimately prove to be less of a wall and more of a door, one that we're just beginning to learn how to open. Chapter 2. The promise of stars within reach. The vastness of space has always defined our most profound limitation. We gaze at stars knowing they remain forever beyond our grasp. Distant lights we can observe but never touch. Worlds we can imagine but never explore. This isolation shapes our existential reality. We are confined to a single world in an immeasurable cosmos, like islanders who can see distant shores but lack boats capable of reaching them. Our current rocket technology, impressive as it is, remains woefully inadequate for interstellar travel. Even reaching our nearest stellar neighbor, Alpha Centauri, would require tens of thousands of years with conventional propulsion. The problem isn't merely technological, it's woven into our understanding of physics. Einstein's special relativity established that as objects approach light speed, they require exponentially more energy to accelerate further. To reach light speed itself would require infinite energy, making it a true cosmic speed limit. This principle has stood for over a century, reshaping our understanding of the universe while seemingly closing the door on interstellar exploration. But what makes the new theoretical approaches so compelling is that they don't try to break Einstein's speed limit. Instead, they work within established physics to find paths around it, suggesting that the cosmos may be more accessible than we thought. Consider what it would mean if these theories proved practical. Suddenly, the thousands of recently discovered exoplanets would transform from abstract data points into potential destinations. The galaxy becomes a neighborhood rather than an unreachable expanse. For a species defined by exploration, from our earliest ancestors leaving Africa to modern astronauts venturing into orbit, faster-than-light capability would represent our greatest journey yet. It would fundamentally change our cosmic perspective. We evolved on a single planet, our minds and cultures shaped by terrestrial horizons. But our telescopes have revealed a universe of staggering diversity and scale. Billions of galaxies, each containing billions of stars and countless worlds. This knowledge creates a tension in the human experience. We can see farther than any previous generation, yet the distances remain so vast that they render direct exploration seemingly impossible, confining us to our cosmic neighborhood. The promise of faster-than-light travel isn't merely technological, it's deeply philosophical. It challenges us to reconsider our place in the universe, suggesting that we might not be forever bound to our birth world. Throughout history, new transportation technologies have transformed human societies. From the first sailing ships that connected continents to aircraft that turned day-long journeys into hours, mobility has expanded our horizons and reshaped our cultures. Faster-than-light travel would represent the ultimate expansion of human reach. It would open the possibility of a multi-stellar civilization, with all the diversity of environments, resources, and perspectives that would entail. Such technology would also transform our search for extraterrestrial life. Rather than relying on telescopes and radio signals, we could directly explore promising worlds, studying their biochemistry and potential ecosystems up close. The philosophical implications run deeper still. Access to cosmic scales of travel would challenge our conceptions of time, distance, and possibility. It would connect us to the broader universe in ways we can scarcely imagine. For a species that has often defined itself through exploration and discovery, the ability to reach other stars would fulfill a dream as old as our first glances skyward. It would mark a new chapter in human evolution. There's something profoundly comforting in knowing that our cosmic isolation might not be permanent, that the lights we see in the night sky might someday welcome human visitors, that ancient questions might find answers through direct observation. Practically speaking, faster-than-light travel would create a kind of cosmic insurance policy. A spacefaring civilization with access to multiple star systems becomes vastly more resilient, no longer dependent on the fate of a single world. Ultimately, the pursuit of faster-than-light travel reflects something essential about human nature. We've never been content with limitations. From the earliest seafarers who pushed beyond the horizon to modern scientists probing quantum realms, we explore. The theories we'll discuss tonight matter because they represent the quintessentially human drive to question boundaries, to imagine alternatives, and to seek paths forward, even when conventional wisdom suggests there are none to be found. Chapter 3. From Impossibility to Theory. The story of faster-than-light travel begins not with technology, but with imagination. Ancient cultures worldwide told tales of instantaneous travel, gods who could appear anywhere at will, heroes who could traverse vast distances in the blink of an eye. These myths reflected a deep human desire to transcend the limitations of distance. From flying carpets to seven-league boots, folklore across cultures envisioned means to overcome the tyranny of space that confined human movement. The scientific consideration of extreme cosmic speeds began in earnest with Einstein's 1905 paper on special relativity. In establishing the relationship between mass, energy, and the speed of light, Einstein inadvertently created what seemed an insurmountable barrier. His equations showed that as objects accelerate toward light speed, they gain mass, requiring ever-increasing energy for smaller gains in velocity. At light speed itself, an object's mass would become infinite, requiring infinite energy, a physical impossibility. This cosmic speed limit wasn't just a technological hurdle, but a fundamental principle of reality. Unlike sound barriers that engineering could overcome, the light barrier appeared absolute, woven into the very fabric of spacetime itself. For decades following Einstein, faster-than-light travel remained firmly in the realm of science fiction. Serious physicists rarely discussed it, considering it settled science that such travel was impossible according to our understanding of physical law. Science fiction, meanwhile, invented workarounds. Star Trek's warp drive, Asimov's hyperspace jumps, and countless other fictional technologies helped us imagine cosmic travel without concerning ourselves with the limiting equations of relativity. The first serious scientific reconsideration came in 1994 when Mexican physicist Miguel Alcubierre published a paper titled The Warp Drive, Hyperfast Travel Within General Relativity. Its premise was revolutionary, yet grounded in established physics. Alcubierre's insight was elegant. Rather than trying to move an object faster than light through space, what if we moved space itself? General relativity places no speed limit on the expansion or contraction of spacetime. His mathematical model described a warp bubble that would compress space in front of a spacecraft while expanding space behind it. The ship itself would remain stationary relative to its local spacetime, never breaking the light speed barrier. Imagine a surfer riding a wave. The surfer isn't propelling themselves forward. They're being carried by the wave's movement. Alcubierre's concept suggested spacecraft could similarly ride a wave of compressed spacetime. The mathematics checked out. Alcubierre had found a theoretical loophole in Einstein's cosmic speed limit, one that didn't violate relativity, but worked within its framework. The concept was revolutionary, but it came with significant caveats. Creating such a warp bubble would require negative energy, essentially matter with negative mass, something we've never observed in nature and aren't sure can exist. It would also require enormous amounts of this exotic material. Early calculations suggested that creating even a modest warp bubble would require more energy than exists in the observable universe. The theory was mathematically sound, but seemingly physically impossible to implement. For years, the Alcubierre drive remained a fascinating thought experiment, theoretically possible but practically unfeasible. Then, in 2011, physicist Harold White at NASA announced a significant revision to the energy requirements. White's calculations suggested that by modifying the shape of the warp bubble from flat to donut-shaped, the energy requirements could be drastically reduced, potentially to the mass energy equivalent of an object the size of the Voyager spacecraft. This was still well beyond our current capabilities, but represented a reduction from more energy than exists in the universe to extremely difficult but not fundamentally impossible. The door to serious research had cracked open. Meanwhile, quantum physicists were exploring other phenomena that seemed to challenge our understanding of space and distance. Quantum entanglement demonstrated that paired particles could influence each other instantly across any distance. Einstein himself called this spooky action at a distance, and considered it a paradox that revealed flaws in quantum theory. But subsequent experiments confirmed entanglement's reality, suggesting space might be more malleable than we'd thought. These developments converged in the early 21st century to create renewed scientific interest in what had once been dismissed as impossible. Theoretical physics papers exploring various faster-than-light concepts began appearing in respected journals. From these beginnings, researchers have continued refining theories of space manipulation, drawing on advances in quantum physics, string theory, and other cutting-edge fields to explore what once seemed firmly in the realm of science fiction. Chapter 4: The Physics of the Seemingly Impossible. To understand the new approaches to faster-than-light travel, we must first grasp the true nature of space. Far from being empty nothingness, space is a dynamic entity, a flexible medium that can stretch, compress, and curve in response to mass and energy. Einstein's general relativity revealed that what we perceive as gravity is actually the curvature of spacetime caused by massive objects. Planets don't orbit the sun because of a force reaching across space, but because they follow the curves in spacetime created by the sun's mass. This fundamental insight, that space itself is malleable, provides the theoretical foundation for potential faster-than-light travel. If space can bend and stretch naturally, perhaps it can be artificially manipulated in ways that effectively bypass the light speed limit. Consider the cosmic scale we're attempting to traverse. Light, traveling at 299,792 kilometers per second, takes 4.2 years to reach our nearest stellar neighbor, Alpha Centauri. Our fastest spacecraft would need about 75,000 years to make the same journey. Our Milky Way galaxy spans roughly 100,000 light-years across, meaning light itself needs 100 millennia to travel from one edge to the other. And beyond our galaxy lie billions more, so many millions of light-years distant. At conventional sublight speeds, even reaching the nearest stars within a human lifetime seems impossible. And yet, the mathematics of general relativity contains no prohibition against the artificial manipulation of spacetime to create shortcuts. The key distinction is between local and global speed limits. While nothing can move through space faster than light, there's no limit to how quickly space itself can expand or contract. The early universe expanded far faster than light speed during cosmic inflation. This distinction offers a potential loophole. If we cannot exceed light speed within space, perhaps we can move space itself, carrying us along like a cosmic conveyor belt. This is the core principle behind the Alcubierre drive concept. Another approach considers Einstein-Rosen bridges, popularly known as wormholes. These theoretical tunnels through spacetime could connect distant points directly, allowing travelers to bypass the vast distances that would otherwise separate them. Mathematically, wormholes are valid solutions to Einstein's field equations, suggesting they could exist. The challenge lies in engineering such structures and keeping them stable enough for travel, problems that remain far beyond our current technological capabilities. Quantum physics offers yet another avenue. Quantum tunneling allows particles to pass through energy barriers that classical physics would deem impenetrable. Some theorists speculate that similar principles might apply at larger scales. Quantum entanglement, which Einstein famously called spooky action at a distance demonstrates that information or influence can appear to travel instantly between entangled particles, regardless of the distance separating them. While we cannot use entanglement directly for faster-than-light communication or travel, its existence suggests our understanding of spacetime at the quantum level remains incomplete. These gaps in knowledge may contain the keys to new forms of cosmic transport. Recent laboratory experiments have demonstrated the malleability of space at small scales. In 2015, scientists at the LIGO Observatory directly detected gravitational waves, ripples in spacetime caused by violent cosmic events, confirming another prediction of general relativity. These observations prove that spacetime can be compressed and stretched by natural processes. The question becomes whether we might harness similar principles artificially at scales and energies we can control for practical transportation. The challenges remain immense. Creating even a microscopic Alcubierre warp bubble would require exotic matter with negative energy density, something we've never observed in nature and aren't certain can exist in the quantities needed. Similarly, stabilizing a wormhole against collapse would require negative energy to counteract the natural tendency of such structures to pinch closed instantly. The energy requirements for either approach far exceed our current technological capabilities, yet the field continues advancing. In 2021, physicists published papers suggesting modifications to the original Alcubierre concept that might significantly reduce its energy requirements. Others have proposed alternative geometries that might be more practical to engineer. The history of science reminds us that impossible is often merely not yet understood. From heavier-than-air flight to quantum teleportation, many achievements once deemed physically impossible have become reality through deeper understanding and technological innovation. The quest to overcome light speed isn't merely about faster travel. It's about testing the boundaries of physical law and expanding our understanding of the universe. Even if practical implementation remains distant, the theoretical work enriches physics today. Consider the vast cosmic distances that currently isolate us. Our nearest galactic neighbor, Andromeda, lies 2.5 million light-years away. The observable universe extends roughly 93 billion light-years across, filled with trillions of galaxies beyond conventional reach. These distances have shaped our perception of cosmic isolation. We see distant worlds, but consider them forever beyond our grasp. Yet the emerging physics suggests this perception may be based on incomplete understanding rather than fundamental limitation. As we stand at the frontier of theoretical physics, we find ourselves asking not whether faster-than-light travel is possible, but what undiscovered principles might make it achievable. What fundamental aspects of spacetime have we yet to understand and harness? The story of faster-than-light physics is just beginning. In the next chapters, we'll explore the most promising theoretical approaches in greater detail, examining the experiments already underway and the roadmap to potential breakthroughs that could transform humanity's cosmic future. Chapter 5. When Physics Breaks Its Own Rules. The pursuit of faster-than-light travel reveals a curious tension within modern physics. Our two most successful theories, general relativity and quantum mechanics, each excel at describing different scales of reality, yet they fundamentally contradict one another at extreme conditions. General relativity perfectly explains gravity and the large-scale structure of the universe. It treats space and time as a unified fabric that can stretch, compress, and curve. Its equations have successfully predicted phenomena from gravitational waves to the precession of Mercury's orbit. Quantum mechanics, meanwhile, governs the subatomic realm with unparalleled accuracy. It describes a world of probabilities rather than certainties, where particles can exist in multiple states simultaneously and influence each other instantaneously across vast distances. The contradiction emerges when we try to reconcile these frameworks. General relativity depicts gravity as continuous and deterministic, while quantum physics reveals a reality built on discrete packets of energy and fundamental uncertainty. Both cannot be completely right. This theoretical divide becomes particularly relevant when examining potential faster-than-light travel. The extreme conditions required for such technology would likely inhabit precisely the zone where these contradictions become most apparent. Consider black holes, objects so massive that space itself curves beyond recognition. Near their centers, both quantum effects and gravitational forces become extraordinarily powerful. Our current physics breaks down completely, unable to describe what actually happens there. Similar breakdowns occur when we examine the first moments after the Big Bang or try to understand the nature of dark energy, the mysterious force accelerating our universe's expansion. These are realms where our mathematical models stop providing clear answers. These gaps in understanding aren't merely academic curiosities. They're potential doorways to entirely new physics. History shows that when established theories fail to explain observations, revolutionary discoveries often follow. One particularly intriguing anomaly involves the quantum phenomenon called entanglement. When particles become entangled, measuring one instantly affects its partner, regardless of the distance separating them. This seemingly allows information to travel faster than light. Einstein himself was troubled by this, calling it spooky action at a distance, and considering it evidence that quantum theory was incomplete. Yet repeated experiments have confirmed entanglement's reality, suggesting our understanding of space and time remains inadequate. Another anomaly appears in the expansion of space itself. During cosmic inflation, the period of exponential growth immediately following the Big Bang, space expanded faster than light speed, yet this violated no physical laws because it was space itself that moved. This distinction between movement through space, limited by light speed, and movement of space, seemingly unlimited, creates a loophole that Alcubierre's warp drive theory exploits. If space can naturally expand faster than light, perhaps we can artificially induce similar effects. Recent work at the frontiers of theoretical physics has revealed other potential contradictions. Loop quantum gravity suggests that space itself might be quantized, made of discrete units rather than a continuous medium. This would fundamentally alter how we understand distance. String theory proposes that reality consists of tiny vibrating strings in multiple dimensions beyond the familiar three spatial dimensions we experience. If correct, these extra dimensions might provide shortcuts through space that bypass the limitations of light speed travel. Both theories attempt to reconcile general relativity with quantum mechanics, and both suggest our conventional understanding of space, time, and distance might be incomplete. These theoretical frameworks remain unproven but offer tantalizing possibilities. Then, there's the curious case of the Casimir effect, a quantum phenomenon where parallel conducting plates placed extremely close together experience a small attractive force. This force arises from quantum vacuum fluctuations, essentially negative energy between the plates. This laboratory-confirmed effect is significant because the mathematics of warp drives and wormholes typically require negative energy or negative mass, substances that would possess the opposite properties of conventional matter and energy. While the Casimir effect doesn't provide nearly enough negative energy for macroscopic applications, its existence proves that negative energy effects can occur in physical systems, challenging the assumption that exotic matter needed for faster-than-light travel is impossible. Another anomaly comes from examining the vacuum itself. Quantum field theory predicts that empty space isn't truly empty, but filled with virtual particles constantly popping in and out of existence. These quantum fluctuations contain enormous energy that might be harnessed. Recent experiments with quantum optics have demonstrated that the properties of the vacuum can be manipulated in laboratory settings. While still far from creating warp bubbles, These experiments show that space itself is an active medium that can be engineered. The theoretical puzzles extend to the nature of time itself. Einstein showed that time can dilate, flow at different rates depending on gravity and velocity. But some physicists now question whether time is fundamental at all or merely emerges from more basic quantum processes. If time is emergent rather than fundamental, our understanding of causality, the principle that causes must precede effects, might require revision. Such reconsideration could open new conceptual approaches to the faster-than-light problem. Perhaps the most provocative anomalies come from cosmology. Observations suggest our universe's expansion is accelerating due to dark energy, a mysterious force constituting roughly 68% of the cosmos, yet completely unexplained by current physics. Similarly, dark matter, which comprises about 27% of the universe, exerts gravitational influence yet doesn't interact with light. Together, these dark components make up 95% of everything, suggesting our understanding of physics remains profoundly incomplete. Some theorists speculate that these mysterious substances might possess exotic properties relevant to space manipulation. If dark energy can naturally accelerate cosmic expansion, perhaps similar principles could be harnessed for technological applications. The expanding field of quantum gravity continues to yield surprises. Recent theoretical work suggests that spacetime might not be fundamental, but emerges from quantum entanglement. If correct, this would revolutionize our understanding of distance and could provide new approaches to faster-than-light travel. What makes these anomalies so tantalizing is not just their individual significance, but their convergence. They collectively point toward a deeper reality where space, time, energy, and matter behave differently than our intuition suggests. A reality where faster-than-light travel might not be impossible after all. As we continue exploring these contradictions and anomalies, we're not merely seeking technological capabilities, but deepening our understanding of reality itself. The quest for faster-than-light travel has become inextricably linked with the quest to reconcile our most fundamental theories. Chapter 6. What we get wrong about cosmic shortcuts. Popular culture has embraced faster-than-light travel as a storytelling staple. From Star Trek's warp drive to Star Wars' hyperspace jumps, these fictional technologies shape public expectations, often leading to misconceptions about what actual physics might eventually permit. Perhaps the most common myth is that scientists are seeking ways to break the light speed barrier, as if we merely need more powerful engines to push through some cosmic wall. This fundamentally misrepresents the theoretical approaches being seriously considered. Current research doesn't aim to exceed light speed within normal space. Einstein's prohibition against this remains solid. Instead, researchers explore ways to work within established physics to effectively bypass the limitation through space manipulation or quantum effects. Another widespread misunderstanding is that faster-than-light concepts are purely speculative with no foundation in mainstream physics. In reality, the mathematics behind warp drives and wormholes derives directly from Einstein's field equations, the same equations that successfully predict gravitational waves. Many believe the primary barrier to such travel is technological, that we simply lack sufficiently advanced engineering. While technology certainly presents challenges, the deeper obstacles involve fundamental physics questions about negative energy, exotic matter, and quantum gravity. Popular science often simplifies wormholes as tunnels through space, but this visualization can be misleading. A more accurate description would be connections between different points in the spacetime manifold, essentially geometric shortcuts through the fabric of reality itself. Similarly, discussions of the Alcubierre drive often describe it as surfing on a wave of compressed space. While intuitive, this metaphor doesn't capture the complexity of the four-dimensional space-time geometry involved, or the exotic matter requirements. A persistent myth suggests that quantum entanglement could enable faster-than-light communication. Despite the spooky action at a distance, entanglement cannot transmit usable information faster than light due to the random nature of quantum measurement outcomes. This limitation is known as the no-communication theorem in quantum physics. While entangled particles do influence each other instantaneously across any distance, this influence cannot be controlled to transmit messages, making it unsuitable for practical communication. Some speculative writers suggest that existing physics already contains proven faster-than-light phenomena. They point to quantum tunneling, where particles appear to traverse barriers instantaneously. Careful analysis, however, shows that no information actually travels faster than light. In tunneling experiments that initially appeared to show superluminal speeds, the leading edge of quantum wave functions still respected the cosmic speed limit. The apparent faster-than-light effect comes from the probabilistic nature of quantum mechanics, not actual superluminal motion. Another common misinterpretation involves Einstein's famous equation E equals mc. Some suggest it proves faster-than-light travel is impossible because objects would require infinite energy at light speed. While correct for conventional acceleration, this doesn't apply to space manipulation approaches. Many assume that faster-than-light travel would necessarily allow time travel, creating paradoxes like the grandfather paradox. While certain faster-than-light scenarios could theoretically allow backward time movement, others specifically avoid this issue through careful spacetime geometry. Alcubierre's warp drive, for instance, could be constructed to prevent closed time-like curves, paths through spacetime that return to their starting point in time. This would enable faster-than-light travel without the paradoxes associated with time travel. The term warp drive itself creates misconceptions. Borrowed from science fiction, it suggests more certainty than currently exists. Scientists typically use more precise terminology like spacetime metric engineering or Alcubierre metric to describe these theoretical concepts. Visual representations of wormholes and warp bubbles often show simplified three-dimensional models that fail to capture their true four-dimensional nature. These visualizations can create misunderstandings about how such phenomena would actually function if realized. A more subtle misconception involves causality, the principle that causes must precede effects. Some assume faster-than-light travel necessarily violates causality. However, certain theoretical frameworks maintain causal relationships while still allowing effective superluminal transit. For instance, if faster-than-light travel occurs within a preferred reference frame, like that defined by the cosmic microwave background, it could potentially avoid causality violations that would otherwise occur in special relativity with arbitrary reference frames. Many believe that negative energy or negative mass, requirements for many faster-than-light theories, are purely theoretical constructs with no connection to observable reality. Yet phenomena like the Casimir effect demonstrate that negative energy densities can exist in physical systems. Similarly, some dismiss the possibility of manipulating spacetime because it seems too exotic for practical engineering. Yet we already observe natural spacetime manipulation in the form of gravitational lensing, where massive objects bend light paths by curving the space around them. The distinction between breaking physical laws and finding loopholes within them is crucial. Nature doesn't forbid exceeding the speed of light. It forbids accelerating to light speed within normal space. This leaves open possibilities that work within established physics. Many discussions of faster-than-light travel assume it would require new physics beyond our current understanding. While this may prove true, it's equally possible that solutions exist within current frameworks that we haven't yet fully explored or understood. Einstein himself changed his views on what physics permitted throughout his career. Many concepts he initially rejected, like black holes and the expansion of the universe, are now mainstream physics. Scientific understanding constantly evolves as theories develop and evidence accumulates. Perhaps the most pervasive myth is that faster-than-light travel belongs exclusively to science fiction rather than serious scientific inquiry. In reality, peer-reviewed journals regularly publish papers examining these concepts within rigorous theoretical frameworks. The NASA EagleWorks laboratory, for example, has conducted experimental investigations into the feasibility of the Alcubierre metric. While preliminary and limited in scope, such research demonstrates that faster-than-light concepts receive legitimate scientific attention. Ultimately, the distinction between informed speculation and established science remains crucial. While faster-than-light theories derive from mainstream physics, they remain hypothetical until experimental evidence confirms their viability, a standard that applies to all scientific advancement. Chapter 7. If we could reach the stars. The implications of achieving faster-than-light travel would extend far beyond transportation technology. They would fundamentally transform our relationship with the cosmos and potentially alter the trajectory of human civilization in ways we are only beginning to imagine. Consider our current cosmic isolation. Humanity exists on a single planet orbiting an ordinary star in one galaxy among billions. Even with extraordinary advances in conventional propulsion, we remain effectively trapped within our solar system due to the vast interstellar distances. This isolation creates an existential vulnerability. Any planetary-scale catastrophe, from asteroid impacts to climate disaster, threatens our entire species. We keep all our metaphorical eggs in one planetary basket, with no practical means of establishing self-sustaining communities elsewhere. Faster-than-light travel would fundamentally change this equation. Suddenly, the thousands of potentially habitable worlds astronomers have identified would become accessible destinations rather than distant data points. Humanity could spread across multiple star systems. This dispersal wouldn't merely provide insurance against extinction. It would create unprecedented opportunities for human development as communities adapted to different environments, face novel challenges, and develop distinct cultures and perspectives. The history of human exploration suggests that when geographic isolation ends, cultural exchange and innovation accelerate. The ancient Silk Road, oceanic exploration, and digital communication each transformed human societies. Interstellar connections would likely catalyze even greater transformations. From a scientific perspective, faster-than-light capability would revolutionize astronomy and planetary science. Instead of relying solely on remote observations, we could directly study distant phenomena, from black holes to exoplanet atmospheres, gathering data no telescope could provide. Consider what we might learn from visiting other solar systems. We currently base our understanding of planetary formation on a single example, our own system. Direct observation of hundreds or thousands of star systems would transform our comprehension of cosmic evolution. The search for extraterrestrial life would similarly transform. Rather than detecting ambiguous biosignatures from afar, we could directly sample alien environments, perhaps discovering life forms based on entirely different biochemical principles than Earth's carbon-based biology. Such discoveries would provide unprecedented insight into life's fundamental nature. Are DNA and proteins universal, or merely one solution among many? Does evolution follow similar patterns regardless of biochemistry? Direct observation would answer questions we can currently only speculate about. The economic implications would be equally profound. New worlds would offer resources beyond imagination, not just precious metals and minerals, but entirely novel materials, compounds, and biological products with applications we cannot currently envision. Energy production might transform as well. Access to multiple star systems could enable stellar engineering on scales currently relegated to theoretical physics. Structures like Dyson swarms, constellations of solar collectors surrounding stars, might become practical megaprojects. For individual human lives, faster-than-light travel would reframe our temporal perspective. Currently, The knowledge that we can never personally witness cosmic events beyond our immediate vicinity creates a sense of limitation, of being trapped in both space and time. Imagine instead the possibility of witnessing a supernova firsthand, observing the formation of planetary systems, or studying the dynamics of galactic cores. Events that unfold over timescales far beyond human lifespans would become accessible through spatial mobility. The philosophical and religious implications would be equally significant. How would our spiritual traditions incorporate the discovery of other worlds, potentially with their own intelligent species? What would it mean for our cosmic perspective to encounter truly alien minds? Throughout history, revolutionary transportation technologies have reshaped human societies in unpredictable ways. The domestication of horses, the invention of sailing ships, railways, automobiles, and aircraft each transformed not just how we move, but how we live, work, and think. Faster-than-light travel would represent a similar inflection point, but at a cosmic scale. It would effectively shrink the universe, making distant realms accessible, just as earlier transportation revolutions shrank our planet and connected previously isolated cultures. Consider, too, the impact on human conflict and cooperation. Would access to countless new worlds reduce resource competition and territorial disputes? Or would it simply extend existing geopolitical tensions to interstellar scales? Both outcomes seem plausible. History suggests that frontiers often provide opportunities for new social and political arrangements, spaces where innovative systems can develop away from established power structures. An interstellar frontier might offer similar opportunities for human political experimentation. The military implications cannot be ignored. Faster-than-light technology would create unprecedented strategic capabilities and vulnerabilities. Nations or organizations with such technology would possess mobility advantages beyond anything in human history. This potential for conflict underscores the importance of developing ethical and governance frameworks alongside the technology itself. How would we manage access to faster-than-light capabilities? What principles would guide human expansion beyond our solar system? Perhaps most profoundly, faster-than-light travel would transform our temporal horizon. Currently, human planning rarely extends beyond decades or centuries. The effective isolation of distant future generations limits our investment in truly long-term projects. Interstellar mobility would connect us to future timeframes in new ways. Projects spanning centuries or millennia become more conceivable when we can envision our descendants witnessing their completion, even if we ourselves cannot. The possibility also raises questions about human evolution. Communities separated by interstellar distances might eventually develop into distinct subspecies or even separate species, creating a branching tree of human evolution across the stars. From an existential perspective, faster-than-light capability might answer one of our most profound questions. Are we alone in the cosmos? Direct exploration would finally resolve whether intelligent life is common or rare, whether we are cosmic pioneers or latecomers. The discovery of other technological civilizations would provide unprecedented opportunities for cultural exchange and knowledge sharing. It might also reveal different evolutionary paths, alternative solutions to technological challenges, and novel approaches to cosmic questions. Conversely, if extensive exploration revealed no other technological species, this great silence would carry profound implications. It would suggest that advanced technological civilization might be extraordinarily rare, increasing humanity's responsibility as potential caretakers of cosmic consciousness. The immediate practical applications would transform astronomy and astrophysics. Currently, we observe cosmic phenomena with significant time lag, seeing distant galaxies as they existed billions of years ago rather than their present state. Faster-than-light travel would enable real-time observation across vast distances, effectively allowing us to study cosmic evolution as it happens rather than piecing together historical snapshots. our understanding of universal processes would deepen immeasurably. For planetary science, the implications are equally revolutionary. Rather than relying on remote spectroscopic analysis, we could directly sample exoplanet atmospheres, surface materials, and potential biological systems, transforming conjectures into empirical knowledge. All these possibilities remain theoretical, while faster-than-light travel exists only in mathematical models. Yet history repeatedly shows that theoretical breakthroughs often precede practical applications by decades or centuries. From Faraday's early experiments with electricity to Einstein's photoelectric effect, fundamental discoveries frequently yield technological revolutions that their originators could scarcely imagine. The theoretical work on faster-than-light physics may follow a similar trajectory. As we stand at the frontier of these possibilities, we find ourselves in a moment of extraordinary potential. The mathematics suggest doorways in the fabric of reality that might connect distant stars. The engineering challenges remain formidable, perhaps prohibitive with current technology. Yet the theoretical framework continues to develop, suggesting that what once seemed absolutely forbidden by physics might instead be conditionally possible within carefully constructed parameters. The door to the stars remains closed, but perhaps not permanently locked. What awaits in the next chapters of this story? Will practical experiments begin to test these theories? Will new mathematical approaches reveal simpler paths to the stars? The answers remain unwritten, but the questions themselves represent one of humanity's most profound scientific frontiers. Chapter 8. The Leading Contenders. As we approach the frontier of faster-than-light physics, three theoretical frameworks have emerged as the most promising candidates. Each derives from established physics, yet extends into domains where our current understanding remains incomplete. The first and most mathematically developed is the Alcubierre drive, sometimes called the warp bubble approach. Developed by Mexican physicist Miguel Alcubierre in 1994, this solution to Einstein's field equations describes a method of effective faster-than-light travel without violating special relativity. The concept is deceptively elegant. Rather than accelerating an object beyond light speed through space, which remains forbidden, the Alcubierre metric proposes contracting space in front of a vessel while expanding space behind it. Imagine a ship enclosed in a bubble of modified spacetime. The ship itself never locally exceeds light speed relative to its immediate surroundings. Instead, the distortion of space creates the effect of superluminal travel when viewed from outside the bubble. The mathematics resembles how we understand gravitational waves, ripples in space-time that propagated light speed. Alcubierre's insight was that by carefully engineering the shape of these distortions, one could create a stable traveling wave carrying a spacecraft. Initial calculations suggested prohibitive energy requirements, more than the mass energy of the entire observable universe. However, subsequent refinements by NASA physicist Harold White and others have dramatically reduced these theoretical energy needs. By modifying the shape of the warp bubble from flat to toroidal, donut-shaped, White calculated that the exotic matter requirements might be reduced to the mass energy equivalent of the Voyager spacecraft. Still extraordinary, but not cosmologically impossible. The primary challenge remains the requirement for negative energy or negative mass, essentially, matter with properties opposite to conventional matter. While quantum effects like the Casimir force demonstrate that negative energy densities can exist, generating and controlling them at macroscopic scales remains theoretical. Recent papers have suggested ways to potentially stabilize an Alcubierre metric without negative energy, though these approaches remain highly speculative and mathematically incomplete. If validated, they would represent a significant breakthrough. The second major theoretical approach involves Einstein-Rosen bridges, more commonly known as wormholes. These hypothetical tunnels through spacetime could connect distant regions directly, creating shortcuts that effectively bypass light speed limitations. Unlike the Alcubierre drive, which manipulates space along a continuous path. Wormholes would puncture through spacetime, creating a tunnel that might reduce journeys of thousands of light years to negligible distances. Wormholes emerge naturally from Einstein's field equations and have been studied extensively since the 1930s. Mathematically, they represent valid solutions in general relativity, suggesting they could theoretically exist. The challenges are substantial, however. Natural wormholes, if they form at all, would collapse instantly unless stabilized by exotic matter with negative energy density. They would also be microscopic, requiring enormous energy to enlarge to macroscopic scales. Additionally, radiation and gravitational effects near a wormhole entrance would likely be extreme, potentially destroying any matter attempting to traverse it. Theoretical work continues on how these effects might be mitigated through careful engineering. Some physicists have proposed that carefully arranged configurations of exotic matter might create traversable wormholes stable enough for macroscopic objects to pass through. The mathematics checks out, but the practical implementation remains far beyond current capabilities. The third leading approach explores quantum phenomena that might enable effective faster-than-light transit. This framework is less developed mathematically than the other two, but draws on emerging understanding of quantum gravity and spacetime emergence. Quantum entanglement, Einstein's spooky action at a distance, demonstrates that quantum systems can maintain instantaneous connections regardless of separation distance. While this cannot directly transmit information faster than light, it suggests space itself might have quantum properties. Recent theoretical work in quantum gravity proposes that spacetime might not be fundamental, but emerges from more basic quantum processes. If correct, this could reveal new approaches to space manipulation that aren't apparent in classical general relativity. Some speculative models suggest that quantum tunneling, a phenomenon where particles can traverse energy barriers that would be classically impassable, might be applicable to macroscopic systems under specific conditions, potentially allowing transit through space in ways that appear superluminal. These quantum approaches remain the most speculative of the three frameworks, but potentially the most revolutionary. If spacetime itself emerges from quantum entanglement, as some theories suggest, then the barriers to faster-than-light travel might be conceptual rather than physical. Each of these approaches faces substantial theoretical and practical challenges. The Alcubierre drive requires exotic matter and enormous energy manipulation. Wormholes need similar exotic materials, plus solutions to intense gravitational and radiation effects. Quantum approaches, while potentially revolutionary, remain mathematically underdeveloped and lack clear pathways to practical implementation. They represent promising directions for research rather than well-formed theories at this stage. Despite these challenges, all three frameworks share a crucial characteristic. None directly violates established physical laws. Each works within the mathematics of either general relativity or quantum theory, seeking loopholes rather than contradictions. This distinction is crucial for scientific credibility. Unlike speculative concepts that simply ignore established physics, these approaches derive from our most successful physical theories while exploring their boundaries and intersections. In recent years, theoretical work has increasingly focused on the convergence of these approaches. Some physicists propose that the mathematics of warp drives, wormholes, and quantum spacetime manipulation might represent different perspectives on the same underlying phenomena. For instance, certain quantum effects might provide the exotic matter needed for both Alcubierre drives and wormhole stabilization. Similarly, the spacetime distortions of warp drives might be more easily achieved through quantum manipulation of spacetime's emergent properties. As theoretical understanding deepens, these distinct approaches may reveal themselves as complementary rather than competing. Different mathematical descriptions of the same underlying physics, each illuminating aspects the others obscure. Chapter 9. New Eyes on Ancient Light. The theoretical foundations for faster-than-light travel continue developing. But equally important are the revolutionary observational tools now coming online. These instruments don't directly test faster-than-light theories, but they deepen our understanding of the cosmic conditions where such theories operate. The James Webb Space Telescope, launched in 2021, represents a quantum leap in our ability to observe distant cosmic phenomena. Its unprecedented infrared sensitivity allows scientists to peer through cosmic dust clouds and observe the most distant ancient galaxies in unprecedented detail. While JWST doesn't directly investigate faster-than-light physics, its observations of early cosmic structures, dark matter distributions, and exotic astronomical phenomena provide crucial data about spacetime's behavior under extreme conditions. By revealing how the earliest cosmic structures formed and evolved, JWST helps constrain theoretical models of dark energy and dark matter, the mysterious components that comprise 95% of our universe and potentially hold keys to space manipulation. Similarly, the Event Horizon Telescope, a planet-scale array of radio telescopes that captured the first image of a black hole in 2019, provides unprecedented data about gravity's extreme effects on spacetime, precisely where general relativity approaches its limits. Black holes represent cosmic laboratories where spacetime curvature reaches maximum values. Understanding their detailed structure and behavior helps theorists refine models of how spacetime might be artificially manipulated for transportation purposes. The detection of gravitational waves by LIGO and Virgo observatories marks another revolutionary advance. These ripples in spacetime, produced by violent cosmic events like merging black holes, provide direct evidence that spacetime is dynamic and malleable. Each gravitational wave detection adds to our understanding of how energy interacts with the fabric of spacetime, knowledge directly relevant to the artificial spacetime distortions proposed in faster-than-light theories like the Alcubierre drive. Neutrino observatories like IceCube at the South Pole and Super Kamiokande in Japan detect nearly massless particles that interact only weakly with normal matter. These instruments reveal properties of matter and energy under conditions where quantum effects dominate. Understanding neutrinos' behavior helps refine quantum field theories that might eventually explain how negative energy or exotic matter, critical components of many faster-than-light concepts, could be generated and controlled. Alongside these observational advances, new experimental approaches are testing the foundations of quantum mechanics in ways directly relevant to faster-than-light theories. Quantum entanglement experiments increasingly probe the nature of space, time, and causality. Recent experiments have demonstrated quantum entanglement between particles separated by kilometers, confirming that quantum connections transcend spatial separation in ways classical physics cannot explain. These results strengthen the case that spacetime has quantum properties. Other experiments explore quantum superposition at increasingly macroscopic scales, demonstrating quantum effects in ever larger systems. This work helps bridge the gap between quantum mechanics and general relativity, theories that must ultimately converge in any viable faster-than-light approach. Laboratory studies of the Casimir effect, where quantum fluctuations create negative energy densities between closely spaced, provide tangible evidence that the exotic energy states required by faster-than-light theories can indeed exist, albeit at microscopic scales. Some researchers have proposed experimental tests specifically designed to detect Alcubierre-type spacetime distortions. These highly sensitive interferometers would look for minute effects that might reveal properties of spacetime relevant to warp drive physics. White's team at NASA has conducted small-scale experiments using interferometers to search for evidence that microscopic spacetime manipulation might be possible with current technology. While preliminary results remain inconclusive, such approaches begin translating theory into testable science. Particle accelerators like the Large Hadron Collider continue probing fundamental physics at ever higher energies. These experiments don't directly test faster-than-light theories, but help establish the behavior of matter and energy under extreme conditions. The confirmation of the Higgs boson in 2012 validated a crucial aspect of the standard model of particle physics. Future discoveries might reveal particles or fields with exotic properties, relevant to space manipulation or negative energy generation. Cosmological observations provide another crucial source of data. Measurements of the universe's accelerating expansion, attributed to dark energy, reveal that space itself can expand faster than light speed when driven by appropriate energy configurations. This natural cosmic expansion differs from technological applications, but demonstrates that faster-than-light movement of spacetime doesn't inherently violate physics. The challenge becomes understanding and replicating the underlying principles at controllable scales. Theoretical work proceeds alongside these observational and experimental advances. Computational modeling of exotic spacetime geometries has become increasingly sophisticated, allowing detailed analysis of warp bubbles, wormholes, and other proposed faster-than-light mechanisms. These simulations reveal subtleties in proposed faster-than-light metrics that weren't apparent in earlier mathematical treatments. For instance, recent models suggest that certain configurations might reduce exotic matter requirements far below previous estimates. Perhaps most promising is the convergence of multiple research strands. Quantum gravity theories, cosmological observations, and laboratory quantum experiments increasingly point toward a deeper understanding of spacetime as dynamic, quantum, and potentially manipulable. This convergence doesn't guarantee practical faster-than-light travel, but suggests that theoretical barriers are gradually yielding to sustained scientific inquiry. The questions are shifting from, is it possible? To what specific conditions would make it possible? The philosophical implications of this work extend beyond technology. These investigations probe the fundamental nature of space, time, and causality, concepts central to both physics and human experience. If space and time aren't fundamental, but emerge from deeper quantum processes, our entire conceptual framework shifts. Distance itself becomes malleable rather than absolute, potentially opening doors to cosmic connectivity that once seemed permanently closed. Chapter 10. The Doorway in the Equations. After exploring the theoretical foundations, technological challenges, and emerging research, we return to our original question: have scientists truly found a way to travel beyond light speed? The answer requires nuance, combining cautious optimism with scientific humility. The clearest statement we can make is this: contemporary physics contains no fundamental prohibition against effective faster-than-light travel through space-time manipulation. The mathematics of general relativity explicitly allows for such possibilities under specific conditions. This represents a profound shift from the 20th century, understanding that faster-than-light travel was absolutely forbidden by physics. Today's theoretical physics suggests it is conditionally possible, though enormous engineering challenges remain. The Alcubierre metric, wormhole solutions, and quantum approaches all derive from established physical theories. None requires abandoning the core principles of relativity or quantum mechanics. They explore the boundaries and intersections of these frameworks rather than contradicting them. This doesn't mean practical implementation is imminent or even guaranteed possible. The energy requirements remain extraordinary, and generating the necessary exotic matter or negative energy states exceeds current technological capabilities by many orders of magnitude. However, history repeatedly shows that theoretical possibility often precedes practical implementation by decades or centuries. From nuclear energy to quantum computing, concepts once considered impossible have eventually transitioned from mathematics to physical reality. Recent theoretical refinements offer particular cause for measured optimism. Modifications to the original Alcubierre concept have reduced its theoretical energy requirements from more than exists in the universe to potentially achievable levels, though still far beyond current capabilities. Similarly, newer approaches to wormhole stabilization suggest more efficient configurations that might require less exotic matter than originally calculated. These improvements don't solve all challenges, but demonstrate that continued theoretical work yields incremental progress. Perhaps most significantly, our understanding of the quantum nature of spacetime continues to deepen. If spacetime emerges from quantum entanglement, as some theories suggest, entirely new approaches to its manipulation might become apparent that aren't visible in classical physics. The convergence of multiple theoretical approaches suggests we're probing genuine possibilities rather than mathematical artifacts. When different mathematical frameworks point towards similar conclusions, it often indicates underlying physical reality. What makes this field particularly promising is the absence of any fundamental theoretical barriers. Unlike perpetual motion or other physically impossible concepts, faster-than-light approaches through space manipulation don't violate conservation laws or other physical principles. Instead, they operate within established physics while exploring regions where our current understanding remains incomplete. The challenges are practical and technological rather than violations of fundamental physical law. This distinction is crucial. Problems of engineering and energy generation, while formidable, have proven solvable throughout scientific history. Fundamental prohibitions, by contrast, represent permanent barriers that no technology can overcome. The theoretical work continues, accelerating. Each year brings new papers refining these concepts, exploring alternative geometries, and proposing more efficient implementations. This sustained academic interest reflects the field's legitimate scientific standing. Institutional involvement further validates these approaches. NASA's EagleWorks laboratory has conducted preliminary experiments related to the Alcubierre metric. While modest in scope, this represents a significant step from pure theory toward experimental investigation. Multiple universities now host research groups exploring various aspects of these theories. From quantum vacuum fluctuations to exotic spacetime geometries, aspects of faster-than-light physics have entered mainstream academic investigation. The answer to our original question thus becomes clear. Scientists have indeed proposed theoretically valid approaches to effective faster-than-light travel through spacetime manipulation, supported by mathematical models derived from established physical theories. These approaches remain theoretical rather than practical at current technological levels. The engineering challenges, particularly generating and controlling negative energy or exotic matter, exceed our present capabilities by many orders of magnitude. Yet no fundamental physical law prohibits these approaches. The limitations are practical rather than theoretical, potentially surmountable through continued research and technological development rather than permanent barriers to cosmic exploration. This represents a profound shift in our understanding of cosmic possibilities. What once seemed an absolute limitation, the speed of light as an unsurpassable barrier, now appears as a conditional constraint that applies specifically to motion through space rather than manipulation of space itself. The timeline for potential development remains highly uncertain. Optimistic estimates suggest decades of theoretical and experimental work before even small-scale demonstrations might become possible. Practical interstellar applications would require further advances still. Yet the mere existence of these theoretical possibilities changes our relationship with the cosmos. The stars may not be forever beyond our reach. The mathematics of our most successful physical theories contains doorways that might eventually connect us to the wider universe. This possibility doesn't require new physics or abandoning established theories. It emerges from deeper exploration of the physics we already know, probing the boundaries and intersections where general relativity meets quantum mechanics. The practical challenges shouldn't be understated. Generating even small amounts of negative energy for laboratory experiments would represent a revolutionary breakthrough. Scaling such approaches to macroscopic transportation remains a far more distant prospect. Yet similar statements could have been made about nuclear energy in 1905, when Einstein first published E=mc, or about space travel in 1903, when the Wright brothers made their first powered flight. Theoretical possibility often precedes practical implementation by generations. What makes faster-than-light concepts particularly compelling is their foundation in established physics rather than speculative new theories. They represent unexplored implications of our most successful physical frameworks rather than contradictions to those frameworks. As we conclude our exploration of this frontier, we find ourselves in a moment of extraordinary possibility. The mathematics suggest doors in the fabric of reality that might connect distant stars. The engineering challenges remain formidable, perhaps prohibitive with current technology. Yet the theoretical framework continues developing, suggesting that what once seemed absolutely forbidden by physics might instead be conditionally possible within carefully constructed parameters. The door to the stars remains closed, but perhaps not permanently locked. As we drift among these cosmic possibilities, suspended between mathematical certainty and technological limitation, we might ask ourselves what it means to live in such a moment, when the stars remain physically distant yet theoretically within reach. Perhaps there is a special kind of wonder in standing at this threshold, where humanity can glimpse pathways to the cosmos while still working to bring those visions into reality. We inhabit the space between what we can imagine and what we can accomplish. Throughout history, such threshold moments have often been the most fertile ground for human creativity and discovery. From early seafarers dreaming of distant shores to quantum pioneers envisioning atomic technologies, the gap between vision and capability drives progress. The equations that hint at faster-than-light possibilities represent more than abstract mathematics. They embody human curiosity, reaching toward the stars, seeking connections across the vast cosmic ocean that separates us from other worlds. Whether these theoretical pathways eventually lead to practical star travel remains uncertain. Yet the quest itself expands our understanding, challenging us to reconsider what we thought impossible and opening new vistas of scientific exploration. Perhaps that is the deepest meaning in these equations, not just the technical possibilities they describe, but the spirit of cosmic exploration they represent. They remind us that the universe may contain more pathways than we've yet imagined. As you drift towards sleep tonight, carrying these cosmic possibilities into your dreams, remember that throughout human history, today's theoretical frontiers have often become tomorrow's new territories for exploration. The stars continue their patient vigil above, neither as unreachable as we once feared, nor as accessible as we might hope. Join us next time as we continue exploring the frontiers where science approaches mystery, where knowledge meets wonder, and where our cosmic journey continues unfolding. Subscribe to Science Asleep for more voyages through the universe's deepest questions, as we journey together through the cosmos and consciousness.